All right. Well, I am so pleased to introduce Dr. John Lekki from NASA, who's going to be talking to us today about quantum communications and aerospace. So let me give you a little background on Dr. Lekki. Dr. Lekki is a senior researcher at NASA Glenn Research Center in Cleveland, Ohio. In his 31-year career at NASA, he has had the honor to lead very talented teams in research and development of optical instrumentation and communication systems in multiple areas, including quantum information systems, hyperspectral remote sensing, integrated vehicle health management, and multiple flight instruments. Dr. Lekki serves as a principal investigator for NASA GRC Quantum Communication Research Team. He also had the privilege to contribute to NASA in an interagency strategic planning for quantum communication. In his support of Earth science, he initiated a joint NASA NOAA research project to develop and utilize the airborne hyperspectral imager to remotely identify harmful algae blooms in the Great Lakes. He currently is the principal investigator for the project development and hyperspectral remote sensing for CubeSat focused on water quality monitoring. In support of the integrated vehicle health management, Dr. Lekki also served as principal investigator for the Vehicle Integrated Propulsion Research VIPR project. Dr. Lekki, it's an honor to have you join us today. Over to you.
Okay, thank you, Karen. Okay, so so I just want to talk briefly about quantum communications in aerospace and give you kind of an idea of what vision or what applications that we're thinking of from a NASA perspective, and just give you a feel for some of the capabilities that we see that we would need to enable quantum communications in aerospace, and then also some of the capabilities that we're developing at NASA Glenn that would support this endeavor. So again, we're up at NASA Glenn up in Cleveland today. It's snowy Cleveland, Ohio, and we focus on NASA's mission is directed towards science, technology, developments in aeronautics and space exploration. And so we have a very, I guess, great mission and goal that we get to support. So it's always an exciting thing to be able to work towards these goals. So in terms of how we potentially see that quantum communications would impact the agency or the nation, there are a couple different categories that we see that as a potential. And all this comes from the literature. These are from papers that have been written about quantum communication networks and how they might be useful. And so a couple of the ideas is quantum communications might be used for security, and maybe you would use that for doing secure monetary transfers. Also, quantum communications, we could do something called we could develop synthetic sensor networks where we're doing entanglement distribution, and actually across the board, entanglement distribution is typically what we're mainly talking about when we're talking about quantum communications. We want to be able to entangle a quanta in one place with a quanta in another place, and then utilize that for these different purposes. So potentially you could entangle sensors, and that could give us a very high sensitivity sensor system where we might want to be able to make some of these measurements that are very difficult. And then likewise, the third, I guess, the third area is this idea of having quantum computers and then having people to be able to remotely access the quantum computers. And quantum computers have strong advantages for doing quantum chemistry problems. So perhaps researchers would, in one research institution, would want to be able to log into a quantum computer and securely be able to work towards developing a new medicine or new materials, something like that. So that's kind of a quantum internet vision. So those are the three different areas, and this kind of summarizes these three blocks over here, summarize those three different areas. The idea of having quantum enhanced sensor arrays where we're distributing entanglement to different sensors, having something like a quantum internet where folks are logging in and performing quantum calculations on quantum computers, or we have distributed quantum computing. And then what we categorized under enhanced communication capability is the idea of using quantum entanglement to secure communication links. One of the, I guess, an illustration of potentially how quantum could impact sensing, and this would be something very interesting from NASA application, is this is a classical image up here to the upper right. This is a image from the Event Horizon Telescope collaboration, which is the first image that we've ever had of a black hole. And it's super exciting, and it's just an amazing image to see. This image was created by the collaboration recording RF telescope data at various RF telescopes. And then they took the data and they brought it back to a central location, and they processed it, and they were able to create this synthetic array that's an aperture almost the size of the planet. And by having that synthetic array, they're able to image the black hole for the first time. Now, that's something we can do with RF in the classical domain because we can record the waveforms. But that's not possible. We can't record the waveforms in the optical domain. So you'd have to use a different technique to be able to do that. And one of the techniques that really looks very interesting and promising is this idea of distributing entanglement to two separate or to multiple separate telescopes. And you would have something called a very long baseline interferometer. And this is the same sort of idea that was done with the RF telescope. But you can imagine with an optical telescope, you can really get the sensitivity scales with inversely with the wavelength. So as the wavelength gets smaller, your sensitivity gets better. So you can imagine that we would be able to see objects that are potentially very, very small and very, very interesting. So it's another idea, just something that we want to think about in terms of these ideas of sensor networks. Now, like I mentioned, the very long baseline interferometry, but you could also entangle or tie together different sensors. You could have atomic vapor sensors that are sensitive to magnetic fields, and perhaps you could create an array that could give you better sensitivity of magnetic fields for a planet. Likewise, atomic clocks are sensitive to gravitational fields. NIST has made amazing progress in atomic clocks where they're so sensitive they can detect just a couple centimeters of movement. If you raise it up a couple centimeters from a table, you would be able to tell the difference. And so having this ability to perhaps entangle atomic clocks so that you can get more information about mass distribution on planets would be very interesting. And some things that we might want to be looking at from NASA's perspective is looking at aquifers, try to measure the amount of groundwater within a particular area. So this is just an illustration of that, the idea of perhaps tying atomic clocks together, that maybe we can find a cave on the moon. These are really interesting for us in terms of potential places where we could put a habitat that could be protected from the radiation. Okay, so switching over to Aero, the idea of secure communication links is something that we've been also thinking about. And we've had an effort moving towards developing a testbed that does both classical and quantum optical communication from an aircraft. And this idea of perhaps we could utilize quantum communications to be able to systematically load quantum distributed cryptographic keys to UAVs, perhaps this is something that would be helpful for the future UAM development, where you could utilize quantum to perhaps improve communication security. One of the things that I just will quickly mention is, one of the issues to solve is authentication. And perhaps if you tie this together with image recognition, then you can you can identify trusted nodes. Here I was picking a clearly visible, airport as a trusted node. Okay, switching over really quickly to NASA GRC capabilities. We have a fully functional quantum communications analysis suite that allows us to perform dynamic calculations and understand how a quantum network would operate given a certain aperture size, certain types of sources, detectors, the background environment, the refraction in the air. So we can calculate that, and we can do it for both spacecraft, ground systems, and also for aircraft. So this is something where if people, I guess, had people had ideas on a particular component, then we can model how that would impact an overall system. So this is one capability that we have. And also, we're presently standing up at what's called the NASA Quantum Metrology Laboratory. And this is a laboratory where we're going to be doing tests on hardware and software and just all the different components associated with a free space quantum network. I should have focused on this too. There are lots of people looking at terrestrial networks, fiber optic networks, and we really just focus on quantum communication to aircraft and spacecraft. So that's what we would be focusing on in this metrology laboratory. We'd want to really understand the sources and the detectors and items like that. So this is another capability that we are developing at NASA Glenn, and soon we're going to be moving into our aerospace communication facility, which is just about done. I wanted to give folks just a quick idea of some of the things that we need. Generally, we need low size, weight, and power terminals, things that we can get into the air or into space, and that they can handle the shaking and the temperature variations. Integrated photonic circuits that include sources, detectors, and quantum circuits, modulators would move us along substantially in terms of getting to flight capabilities. Likewise, non-cryogenic single photon detectors. Right now we have fantastic single photon detectors, but they're cryogenic and they're pretty bulky, and that turns into be fairly expensive to get into space. Likewise, airborne key distribution systems and platforms, the ability to perhaps generate ad hoc networks, scalable quantum memory. I guess I just won't read through these. Let me pick some of these. Optical beacons that would allow us to align different, an aircraft could perhaps find a beacon to talk to a tower or something like that. Authentication protocols that would allow us to authenticate nodes and confirm that there's not an eavesdropper or something along those lines. And then flight and ground terminals, having fiber optic interfaces to these terminals would really, really improve things. So trying to put some potential even mechanical aspects to work towards. I wanted to just quickly mention that there's a couple different ways to engage with NASA, and this is not this doesn't cover all of them, but I did want to mention that we do have a quantum communications small business technology transfer topic that was out in 2021. I'm not sure the timing yet, if about 2022, but in 2021, we did have 4 awards. We also had a quantum sensors STTR topic. And again, these bring together businesses with research institutions to be able to do research. And we had 2 awards for that. And in our space technology mission directorate, we had 1 award for development of quantum communication technologies. And that one's academia focused. I do have these links for the NASA call for proposals. So if you want to engage with NASA and submit proposals, these are 2 key, websites to go to. The NSPIRES has NASA Roses, which has multiple calls, and that's where you'd find something like the STMD call, where we had 1 award last year. And then the SBIR and STTR were where again you can have small businesses teamed up with academia in the STTR program that's under the sbir.nasa.gov website. And that's all I had. So thanks for your time. I appreciate the opportunity to talk with everyone about quantum communications.
Thank you so much, Dr. Lekki. Okay, everyone, if you could give us just a minute, we will bring back Dr. Lekki as well as Dr. Greg for Q&A. Thank you so much.